Hello, everybody. Come on in. Anybody have any questions? Feel free to ask them while we wait for class to start in 2 minutes. I'm not sure off the top of my head. I'm sure it's pretty homely up there. You can tell these glasses are not clean. Woo. So no questions. Got about a minute left. Again, feel free to ask questions. If your speaker don't work or whatever, feel free to type them in the chat and I'll answer them. Chapter 26 homework and conceptual homework has been posted now in week 6, but that's all that's up there. So you might have to look for equivalent stuff on my YouTube channel until I put some more up there. I think week 5 was fine. I have plenty up there, but week 6 I don't have any videos up there yet. But of course, you can always just do a search in my YouTube channel, which is www.youtube.com/Billy Younger Physics Solutions, with each of the first letters of those words capitalized, B, Y, P, and the first S in solutions, plural. Anyways, go there and then go down to the little search on the right in the sort of in the middle of the screen vertically, as opposed to the top, and then you can just type in 242, and that'll just show you all the courses that have 242 in them, and then you can look for ones that cover chapter 25, ones that cover chapter 26, because in those cases I almost always said, named it with something like chapter 25 or CH26 or something like that. So that should help you. Remember also that some of them are old and they've got of course just a document cam with paper and pencil and really bad Wi-Fi. So if you see it's one of those, you might want to go ahead and go to my Google Docs. And when you look in the actual YouTube channel description of the video, it'll actually have like PHY242N01B or something like that. Do a search for that string of symbols, or at least the date part of it, because you can see some of it's actually date and stuff like that. Do a search for that, because the actual file that goes with it, actual PDF picture of the actual notes that I wrote, are actually there with that name. If you just need it and you can't find it, let me know and I'll send you a copy personally. Just let me know, exactly which video you need help with, and I'll send you the documents. So it's after time for class to start, so I will go ahead and get started. Last time I gave you sort of the theory behind most of the stuff in chapter 25, and even hinted a little bit over chapter 26. Today I'm going to just jump with it and start doing some really quick calculations and show you how they're used. Of course, the examples in the book are good too. So for instance, I'm going to calculate a change in resistance as a result of a change in temperature. In the book, it allows you to actually use 2 resistances of a tungsten item at 2 different temperatures and ask you to find the new temperature. I did that for my lecture class. I've done that in past lectures as well. This time I'm doing something a little different. And I'm trying to just keep on rolling with regards to just solving problem after problem after problem in hopes that I can get a lot done. Hopefully I can get into chapter 26 as well. I'm going to just jump in and use the formulas for resistance when they're in series and resistance when they're in parallel. I'll tell you right now, 1, I derived them in my YouTube channel, so you can look it up there. 2, you can find them in your textbook, so you can look it up there. And 3, they're exactly the opposite of the capacitor formulas. So for instance, when you had capacitors in series, you could replace, let's say, 3 capacitors with one capacitor if the three were in series by just finding one capacitor whose capacitance was given by 1 over that capacitance is equal to 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3. If you solved it for that first capacitance, that would give you the equivalent capacitance of 3 in series. If they were in parallel, they just added. So if you had 3 capacitors, 1, 2, and then 3 in parallel with each other, the total capacitance would be C1 plus C2 plus C3. Well, resistance has the same formulas, but it has them in the opposite. Has them in the opposite order. Specifically, resistances in series just add, and resistances in parallel, the reciprocals add to give the reciprocal. So we're just going to go with those results as if we already know it without having to go through the derivation. So let me go ahead and share my document. Does anybody have any questions before we get started? I asked that already several times, but I just want to make sure. All right, well, let's get started then. So I'm going to share my screen. I apologize, but I wrote out some problems to work, and they turned out to be a little, I wrote them a little too small. So the handwriting is going to be kind of small for you to read. Plus, without thinking, I just wrote them in cursive. So if you're one of those unlucky people that didn't get to learn cursive a little bit, you might be a little intimidated. Don't worry, I will read it out loud. This is on video form, of course, and recorded, and will be posted on the internet as well, so you can find it there. But basically what I'm asking is, what is the total resistance of 1.609 kilometers of number 8 gauge wire if it is made of copper? Anybody recognize the number 1.609 kilometers? It's okay if you don't, but it was actually a mile. So I'm just giving you an idea of roughly how much resistance a mile of number 8 wire would be if it's made of copper. Part B, what is its total resistance if it is made of aluminum? Part C, what if I went to number 10 aluminum instead of number 8? And part D, what if number 12 aluminum was used instead? And you can see that this is a weird thing. This is sort of like some ammunition type stuff will have numbers as they get smaller mean bigger. So that's what's going on with these wires. And you can look them up. You can just do a search for what is the diameter of 10 gauge wire, and you'll find something like the page I found was the American wire standard or something like that. It's AWG basically is where it is, and it has the conductor diameter in inches and millimeters. They actually even give you the ohms per 1,000 feet, which is kind of helpful. But anyways, between that and our formula that we already learned, we should be able to do these calculations. So first off, I just laid my iPad on the keypad. That did not work. So solution. Here's part A. So first off, what we know is that the resistance is directly proportional to the length. In other words, the longer the wire, you can sort of think of it as it's taking away or taking more time to get to the end, just like it takes more time to get to the end of a tunnel if the tunnel is longer. The resistance is inversely proportional to the cross-sectional area. You can sort of think of it as if you're evacuating a city via a tunnel. Obviously, a 4 or 5 lane tunnel, which has a bigger cross-sectional area, would allow a quicker departure than a smaller one. So resistance is the inverse of that, meaning it would be harder if the area went down. So area going down means resistance goes up. So that's why they're inversely related. And then that all is proportional to rho, which is called the resistivity, which is a property of the material. So if it's copper, you have one value of rho. If it's aluminum, you have another value, silver, another value. Your book has a table of these, and I'm going to be making use of some of those excuse me, some of those figures. But the main thing is that resistivity, the rho, which looks like a fancy P, that's a Greek letter rho, and it means resistivity. It's supposed to have units of ohms times meters, and it's on the order of 10 to the negative 8. So that's a common resistivity is 10 to the negative 8 ohm times meters. So let's write down some stuff. So number 8 gauge wire, and it's copper. So I also know that L is 1.609 kilometers. So I'm going to say L equals 1.609 kilometers, which, by the way, as I was hinting to you, that's 1 mile. Okay. But that's also 1,609 meters, which is the unit that I needed in. So I've got that now, 1,609 meters. I do need, of course, to know the diameter of number 8 wire. So let's say D number 8 is equal to, and in this case, I get 3.2639. And that is in millimeters, which of course is equal to, if I wanted to convert that to actual meters, you can say that's 3.2639. That is in millimeters, yes. 3.2639 times 10 to the negative third meters. So we've got that. Later, I'm going to make use of the temperature variation, in which case we'll make use of the constant with alpha, which is called the temperature coefficient of resistivity. So we'll make use of that as well. One other thing I need for this, actually, I should say 2 other things, is I need the resistivity of copper. And the resistivity of copper is 1.68 times 10 to the negative 8. I don't know why I wrote 1 there. Ohm meters. And I will eventually need the one for aluminum as well. So I'm going to say the one for aluminum is 2.65 times 10 to the negative 8. Again, ohm meters. And I'll also go ahead and make use of D number 10 and D number 12. Because those, according to the question, are things I'm going to be asked. So D number 10 is 2.58826. millimeters. And D number 12 is 2.05232. So in terms of what I'm using here, let me stop for a second and share the appropriate screen. And that'll be sort of my citation, if you will. So I'm going to share the screen right here. So this is the website that I'm getting it from. I've actually used this website before. I know the results are right, even though it's somewhat of a page that's been put up for, I don't really know the reasons that it's been put up for, but PowerStream Technology is the one that made the page. So that's kind of nice. But anyways, you can see what it has is the AWG, which is really what the standard of the wire gauge is. And you can see as the gauge gets smaller and smaller and smaller, for instance, 4 zeros has 11.64 millimeter diameter, whereas 10 has 2.588 and 12 has 2.05. So you can see as the numbers get higher and higher, the actual diameter gets smaller and smaller. But anyways, you can see that's the actual page. It's called powerstream.com/wiring. Let's see if I put this away, if that helps. No, that did not help either. I can't get control of anything. And the only thing I'm seeing going on right now is Bill Gates is verifying my Microsoft Outlook, which is taking my bandwidth, and that kind of ticks me off. And I wonder if it's actually caused something to slow down too. Why is it not letting me out of this? Okay, hold on a second, folks. Let's see if I can escape the screen or anything. No, I can't do that. All right, I'm going to try to shut down my computer and log back in. This is obviously going to take away some class time. So I apologize, everybody. I'm going to have to kill the computer and then come back in and hopefully start over from scratch there. Up. Now it's finally doing it. Hold on. So let me see if it works now. All of a sudden, it just started working. And now all of a sudden, Microsoft Outlook wants to open up too. Isn't that helpful? I just wonder. I'm just so happy that Outlook is coming back out here. Force quit. Okay, there you go. All right, so we've got our stuff written down now. I should be able to go without having to worry about anything. Part A is basically what is the total resistance of 1.609 kilometers of number 8 gauge wire if it's made of copper. So I've got everything I need for part A. I just want to calculate R. R has got to be equal to 1.68 times 10 to the negative 8 ohm meters. Notice how the units will work out. I've got 1,609 meters. So that now gives me ohms times meters squared. And then I'm going to divide all of that by the area, which, by the way, area of a circle is pi r squared, but r is d over 2. So I can write it like this. And then I don't have to use the pi r squared. I can use pi d squared over 4. So I'm going to say put a 4 on top. That's because a 4 in the denominator of a fraction in the denominator of this fraction will become a 4 on top. So down here, I'm just going to get pi times, and for number 8, we're talking 3.26. Really, you see the sig figs that I'm using is like 3. So I'm going to go with 4 sig figs instead of worrying about all that stuff. So I'll say 3.264 times 10 to the negative 3 meters, and that's going to be squared. I'm actually surprised at how small that number 10 wire diameter is supposed to be. Or excuse me, that number 8 wire diameter is supposed to be, but I might be misremembering wire. If anybody's an electrician, you're probably more familiar with it, but let me know if you think that's not it. But either way, that's I've checked that site before, and or at least I've seen one just like it, and I thought it's pretty good. So I'm going to do 1.68 times 10 to the negative 8 times 1,609 times 4. And then I'm going to divide that by 3.14159, which obviously I don't need that many of them, but times 3.264 e to the negative, e to the negative 3, only this time I'm going to square that number and enclose my parentheses, and that should give me a whopping 3.231 ohms. Notice how the units worked out. You've got ohms squared times, ohm times meter squared in the top, and then just meter squared in the bottom. So you just get ohms. And in fact, given that our smallest number of sig figs, which all of which were multiplied and divided, so it's really this number of sig figs that matter. So that means the 3.231 is just one extra sig fig. Now, that one was for the copper, and that's part A. So what I'm going to do is write part A here and write this here. Now, I think you can see the difference in between part A and part B is what is the total resistance if it's made of aluminum. So what I'm going to say, and I don't know why I put C sub B there. I meant C sub U. Let's change that. Okay. Sorry, folks. Let's see here. Now, I think you can look at this formula and realize that the resistance of the aluminum for part B is going to be similarly defined. And in fact, all I have to do is say resistance of aluminum is equal to the resistance of copper times the resistivity of aluminum divided by the resistivity of copper. So that way I don't have to do that whole calculation all over again. I'm just basically dividing by 1.68 times 10 to the negative 8, and then multiplying by 2.65 times 10 to the negative 8. In fact, I'm not even going to do the 10 to the negative 8. I'm going to take this number, I'm going to divide it by, or excuse me, I'm going to multiply it by 2.65, and then I'm going to divide it by 1.68. And obviously I expected to get bigger, and in fact it did. So the resistance in this case is 5.096. Carrying one extra sig fig again. And of course, that's sort of the quickest and dirtiest way of doing it, which will help me save time since I had the computer lock up for a second. So that's part B. Part C, what if it's number 10 aluminum instead? So right now, what we've decided is let's go with aluminum and let's see what it would be with number 10. So for this case, the R aluminum, and I should probably subscript these number 8, just so I can look back and see. Now, if I want the resistance of aluminum number 10, then basically it's going to be the same thing as the resistance of aluminum number 8. But notice aluminum number 8 had 3.264 times 10 to the negative 3 being divided to make it. I want to get rid of that 3.264 for number 8 and replace it with 2.588 for number 10. Of course, it's in the bottom, so I got to multiply by it. So what I'm going to do is I'm going to write the diameter of number 10 squared over the diameter of number 8 squared. And that way I never have to go back and do the whole calculation again. So now that I have the 5.096 ohms, all I have to do is replace, and I'm just going to take the mantissa part. By the way, I've used that word before, but I'm not sure I've used it in this class. This portion right here of any scientific notation is called the mantissa. I don't know why I know that. I don't recall ever seeing in any of the textbooks I taught in that was that. And I just somehow came across the word, and I thought it reminded me of praying mantis, so it stuck in my head. So I apologize for knowing random crap that don't mean anything. So anyways, I'm going to get rid of the diameter of the 10, which is 3.264. Well, I'll leave it there. What the heck? 3.264. Remember, it has a times 10 to the negative 3, but that don't matter because that's going to cancel out anyways. And I'm going to replace it with the 2.588. Whoa. I'm going to replace that with the 2.588. Now, in this case, I'm carrying, well, I shouldn't say I'm carrying an extra digit, so I'll just leave it as is without that. And of course, I got to remember to square it or it's not going to work. So I'm going to take this number and say times 3.264 squared. And then I'm going to say divided by 2.588. And I'm going to square that. And I put it in parentheses just to make sure I didn't accidentally square stuff twice. Hopefully y'all are calculating along with me, but I got 8.10. That's 3 sig figs. The next two are 557. So I'm going to just carry an extra sig fig and call it a 6. And that's ohms there. So that's the gauge wire. I am going to circle that. First off, it's part C, and I'm going to box it off so we have the answer like such. Any questions on that? Does everybody understand what I'm doing here with these? Rather than going back and calculating the whole formula over again, I can just do this because the formula is the same in each case. So that was part C. Make sure you ask me questions if you have them. And in fact, I'm going to make sure I put up the chats in case someone tries to chat me a question. Okay, I've now put that up as well, so I should be able to see it over in the side. So no questions so far, anyone? Okay, so part D is basically asking for R aluminum. Whoa, Nelly. For some reason, switched to blue. I want to use red. R aluminum, and this time I'm going to say number 12, which is even smaller diameter. So in this case, I'm going to say basically it is R aluminum. I'll stick with the number 8 because, you know, I might have made a mistake in calculating the number 10. So why not just stick with the other one, which is only have one calculation. So this time I still need to get rid of the 3.264 because that was number 8, but I need to replace it with a 2.052. So I'm going to say times diameter number 8 over diameter number 12, and that will be squared. So in this case, I'm going to get 5.096 ohms times 3.264 over 2.052. That has to be squared, of course. So I'm going to say times 3.264 squared, and then I'm going to say divided by parentheses 2.052 squared, close parentheses, and this should get bigger as well, and I get 12.89. So that's 12.89 ohms. And again, I'm carrying one extra sig fig here, but that hopefully gives you some sense of how to use the R equals rho L over A, but also it gives you a physical feeling for, hey, a mile of wire is really, really low resistance. Look at this, we're doing a whole mile of number 8 wire. And when we use copper, we only got 3.2 ohms. That's really, really teeny. Even the stuff you've been doing in class has been 400, 800, 2200 ohms and stuff like that. So this is a pretty small resistance. And even when I got to the smallest, number 12, which I've seen number 12 ran for instance, for car speakers and stuff like that. So a whole mile of that only has a resistance of 12.89. Now, number 16 is a much more useful one that I've seen more often with car speakers and stuff like that. And but anyways, that gives us some idea. The next question is actually going to ask us some stuff about this. It says, consider the 1.609 kilometers of number 10 copper and aluminum wire. How would their total resistances change if the temperature changed from 20 to 56.7 degrees Celsius? That's kind of a big deal because 56.7 degrees Celsius is the hottest temperature ever recorded on Earth. So I'm going to record number 10 copper, and I'm going to record number 10 aluminum. And I just did number 10 because I like number 10 better than number 11. I mean, literally, that's the answer. So actually, crap, I probably should. I tell you what I'm going to do. I'm going to change it to number 8. That's literally why I did number 10, was because I like number 10. But I think it'd be smarter to change to number 8 because I actually already calculated it for number 8. So let's do this. I'm going to zoom in here, and I'm making an executive decision to call that number and 8. Isn't that wonderful? Look at that. Just the powers of technology. All right. The whole reason is now I can go back and realize that number 10 copper and number 8 copper, excuse me, and number 8 aluminum. Number 8 copper was 2.321, or excuse me, 3.231 ohms. And for aluminum, it was 5.096. Each of those was one extra sig fig. So I went ahead and underlined them so I'd have them. Now this problem just wants to know what happens when you change the temperature. Well, we had two formulas that I mentioned to you guys, and they are, let's do this. They are rho is equal to rho 0 times 1 plus alpha t minus t0. Okay. And technically that looks like a 0, and it is a 0, but it doesn't have to be 0. Ideally, what you want to do in a real engineering problem is you want to find a table with a resistivity as close to the working temperature as you're going to have as possible. So if you're working at 40 degrees Celsius, 44 degrees Celsius, it might be good to find one that is giving you the resistivity at 40 degrees Celsius, and you'd use that as rho 0, even though it's not 0 degrees, right? So the closer you can get for your R0, or for your rho 0, the more likely you are to be accurate. You're somewhat accurate no matter what, but obviously the farther you get, the less accurate you are, unless by some freak of nature, which we know is not true, that they truly are linearly related through all temperatures. So that's one of the formulas, but we want the actual resistance. So the formula I want to use is R is equal to R0 times 1 plus alpha t minus t0. And what I do have is I have that scratch that. I will use the original formula. So this works, but the problem is you have to do something. So I just put a line through it. It does work. I would have to use the row and that sort of thing. But what I do have is I have that the alpha for aluminum, let's write it in red, the alpha for copper, and I have the alpha for aluminum, and the alpha for copper is 0.0068. And the units for that, I think you can probably tell from either one of those equations, the unit for that is Celsius degrees to the -1 power. Now, when we put the degree after the Celsius, that means this number is expected to be multiplied by a subtraction between two Celsius measurements, or it actually works this way as well, a subtraction between two Kelvin measurements, even though they're not, Kelvins aren't measured in degrees. So that's what that degree coming after the C means. If you put it before the C, then it's recording an actual physical temperature. Similarly, the alpha for aluminum is equal to 0.00429. And I don't know why they gave me 3 sig figs on one versus only 2 on the other, but that has the same answer as well. So what I'm going to do is I'm going to use rho equals rho 0, because I forgot, actually I could have used R. Yeah, I could have used R. It would have been fine either way. Yeah, what the heck, I will use R. What I'm saying here is I could actually use the resistivity, the left equation, and get it, or I could use the resistivity or the resistance equation, the right. Since I already have the R's, I am going to use R. So let's say R of copper at 56.7. So what we're doing, notice I wrote right here, note the assumption. So that was what I was talking about a second ago when I said if you're actually doing a real engineering problem, you want to find a table of temperature coefficient of resistivity that's measured as close to the actual temperature as you have as possible. Well, ours is exactly one table, and our table is 20 degrees Celsius. So I'm just going to use that. I could look up on the internet and find other ones that would work better, and that's fine. But I'm going to tell you, in real life, you're definitely going to look for the best temperature closest to the temperature you have, but I'm going to pretend like it's linear all the way from 20 degrees Celsius all the way up to 56.7. And I'm almost 100% sure that that is not going to be the correct alpha for that large of a range, but we're going to go with it anyway. So that's the assumptions, quote unquote, that I'm making. Now, what I did record, remember, was the resistance of the copper. Number 8 copper was 3.231. So I'm going to write 3.231 omega is my resistance. So that's the R0. So this is the one at what we assumed was 20.0 degrees Celsius. We had no reason to believe that. So that's another assumption I'm making here, but I'm just pretending like in that previous calculation, I was going with 20 degrees Celsius and that was the resistivity I used. In reality, I took it from a table that gave me resistivity and temperature coefficient of resistivity at 20 degrees Celsius. So in that sense, I made no assumptions other than assuming that the question was asking for 20 degrees Celsius. Okay. So now what I'm going to do is I'm going to take that and I'm going to multiply it by 1 plus. Now for copper, I have 0.0068 reciprocal Celsius degrees times 56.7 degrees Celsius minus 20.0 degrees Celsius. Okay, so this subtraction is what I was talking about. When you subtract a Celsius from a Celsius, you could call that Celsius degrees as opposed to degrees Celsius. And that's just a little trick we use. This is not something that's like sanctioned by SI and it's a special unit or anything like that. It's just what we do in practice. So I'm just giving it to you. So I've got 3.231 omega times 1 plus, and I'm carrying all this out so you can actually see exactly what happens with the sig figs. I'm going to get 0.0068, leave off the units for just a split second. I'm going to multiply that by 36.7. And I did say I'd leave off the units, so I'm going to leave that off completely. 36.7. Notice that did give me 3 sig figs, but now I'm getting ready to multiply it by 2 sig figs, which is going to spit out 2 sig figs, and that's going to slightly anger me. I don't know why, but it will. 3.231 omega, and then 0.0068 times 36.7. By the way, that was that temperature that I recorded was in the Middle East, like Saudi Arabia or something. So that's where they got that 56.7 is not something. I apologize for my dad. Cosmo. So when I multiply 0.0068 by 1, what I end up getting, or excuse me, by 36.7, what I end up getting is 0.249. That next one's a 5, 6, so I'm just going to call that a 6. And in reality, we're only supposed to have 2 sig figs. So these two guys are going to disappear and we get just basically a pure number here. But notice this 1 is basically, I'll write it this way to make some sense of it. This 1 is basically 1.00 with an infinite number of decimal places. So luckily I get back 3 sig figs on this one. Okay, that's the main reason I took all this extra time to do these steps. So I'm going to say 1 plus 0.24956. And then I'm going to multiply that by 3.231. And this gives me 4.037 ohms is the resistance at 56.7 degrees Celsius. And that's for number 8 copper. Okay, so I'll box this off and write that it's equal to R just so we'll know. Now, the other one they want to know is what's the same thing for aluminum. So I'm going to calculate for aluminum. And in this case, notice it's not something really easy where I can just slip in a nice little number and handle it. No, I can't do that. So I got to suck it up and do the whole thing over again. But now I've explained everything, so that should make it moderately easier. Now, the aluminum was 5.096 ohms for the whole mile of it. Now I'm going to do 1 plus, but here's some of the payoff is that the temperature coefficient of resistivity for for aluminum is a little smaller. So I can write 0.00429, which is a little smaller, like I said, than the one for copper. So that's kind of nice. Now I'm going to do again 56.7 degrees Celsius minus 20.0 degrees Celsius, and box all that off. So now what I get is 36.7 times 0.00429, and this gives me 5.096 ohms times 1 point. Now, in this case, when I multiplied 0.00429 by 36.7, I was technically allowed to have 3 sig figs. So that would be 1.157, carrying one extra 4 there. And notice that is a dimensionless quantity. So that's actually what I get. Now I've got actually 4 sig figs, because when you add the 1, again, the 1 is one with an infinite number of decimal places. So in this case, I actually increase the number of sig figs. So I'm going to multiply this by 5.096. And that gives me, whoa, no. Oops, I know what I did. Okay, I forgot to add the 1 to the 0.157. Now I'm going to say times 5.096. And this time I now get an answer of R is equal to 5.89. Now I had 3 going in and 4 multiplying by it, so I still am only allowed 3. So this is 5.898 is the extra sig fig, and that's ohms, and that's at 56.7 degrees Celsius for number 8 aluminum. Okay, so all of this is equal to R. Now, what I want to show you is, what I'm curious about is how much of a difference that is. So I'm going to do the 5.898, and I'm going to subtract from it the 5.096. And then I'm going to divide by the 5.096. And that gives me a 15.7% increase. So I thought I'd see what the percent increase is for that in copper. So the 4.037, I'm going to subtract from that 3.231, and then divide it by 3.231. And then, of course, move the decimal 2 places to the right. And that gives me, for this case, that actually increased by 24.9% increase. So yeah, I will tell you, my father worked for Dominion Power for 30 years and retired from there. And he told me a lot of what they use is aluminum, specifically because aluminum really can handle the weather pretty well. So can copper, but aluminum's at least was a little cheaper. I think it still is. I know copper is actually kind of expensive right now. My wife has a coworker whose car had the catalytic converter stolen while it was in the parking lot during the day shift in the middle of Chesapeake. So there's obviously some reason for stealing catalytic converters, part of which I know is copper, but there's other metals in there that are worth quite a bit of money. So anyways, switching to aluminum instead of copper actually allowed for a much smaller increase in temperature or increase in resistance over temperature. So that's another helpful aspect regarding aluminum. Any questions on this one or the last one? Okay. The next problem, I'm actually going to build on that again, which is kind of weird, but it says, by that time I realized that I was writing way too small. So now I wrote way too big just to even it out. But consider the two previous problems using number 10 aluminum. In this case, yeah, I'm okay with sticking with number 10 because I'm just doing aluminum. So consider the two previous problems using number 10 aluminum to carry 52.0 amps. Now, what I looked up was I wanted to make sure I wasn't using too many amps for number 10. And that same website suggested that number 10 is allowed to carry up to 55 amps. I'd say 52 is cutting it pretty close. But to be honest with you, if you were really trying to supply power to a house, a typical house takes what we call a 200 amp service. So the pole out on the road, if your house is old enough, there will be a pole out on the road and there will be a wire coming from up on that pole that runs into some part of the side of your house and then runs down the side of your house and goes to basically a meter where the electricians or the Dominion Power people can come out and read that meter and tell how much electricity you used since this time last month or whatever. On the other side of that, your circuit breaker for the whole house, that's called a service entrance, and it's 200 amps is what you typically get. If you actually really needed it, you could get a 400 amp service or a 600 amp, or even the power company is more than happy to charge you more for getting more electricity if you so desire. But anyways, a 200 amp service is the normal one. So what I'm going to do here is I'm going to ask you to calculate the power dissipated, and I'm going to ask you to calculate the power dissipated in the second case, where in the second case, I decreased the amperage by a factor of 10 using a step up transformer for voltage. Step up transformer just means the voltage has been stepped up. In this case, I said 10, I meant 100. In this case, I'm stepping up the voltage by a factor of 100, which steps the current down by a factor of 100. So that's what I'm actually doing here. So first off, I want to say how much power would be lost to heat by taking that number 10 aluminum and carrying 52 amps. Well, what we know is here goes our solution. And by the way, I haven't mentioned this too much. I haven't mentioned it all today, but generally speaking, the power coming from the power company here in America, well, everywhere I know of, but the power coming to our houses is AC. And it turns out that the formula is V equal IR, which is Ohm's law, or P equals IV, and that sort of stuff. Those all work, but they have a little caveat, specifically that the average power is, in fact, instead of I squared R, the average power would be I root mean squared times R. So we are using P is equal to I root mean square V root mean square, which is also, if we plug in Ohm's law, we can say it's I squared, again, root mean square, times R. R, we can do V root mean square squared. In this case, it would be over R, if I remember correctly. Okay. So those are our formulas when we're using AC, by the way. Okay. I'm going to use the second one because that allows me to use the resistance. So for part A, I know that the power loss, just as a result of carrying this amps, is in fact going to be 52.0 amps. That's going to be squared. And then, of course, the number 10, oh crap, I didn't write it down before. So I have to change it again now. The number 10 resistance for aluminum was 8.106 ohms. Carrying 1 extra sig fig. And we'll see what the power loss is. And I think I'm supposed to use, in this case, a distance of 160.9. Notice it was 1.609 before. So I actually have to, given that rho, I didn't mention this before, let me kill this equal sign here. I also have to mention that R is equal to rho L over A, which means R for 100 miles is equal to 100 R 1 mile. So I'm just going to notice if I multiply 1.609 by 100, I get 160.9. So that's why I'm putting this 100 right here. And this is per mile here. And this is miles there. It doesn't matter that I'm using miles because they're actually, the units are canceling out. So I multiplied 52 squared times 8.106 times 100. And in this case, I get 2.19, 2.191 or 192, excuse me, times 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6 watts. So that's how much power is dissipated just by heat. Yes, Michael, go ahead.
What does the RMS mean?
Okay, very good question. I sort of mentioned this haphazardly before last class, but basically what's going on here with AC, the voltage or the current, whichever one you want to do, is actually equal to V0 times, let's say, sine of 2 pi times the frequency times time. And you could put a phase angle in here so it don't line up perfectly. In other words, it wouldn't look just like sine, but in this case, we're going to just keep it. So this is sine right here. And this is one period of the wave. So that particular time would be basically 2 pi over the period, where F, the frequency, is 1 over the period. And in America, the frequency we use is 60 hertz. So 1 divided by 60 would be the actual period. But the main thing is that's what the current does. It wiggles back and forth. If you tried to take the average voltage of this, it would be 1 over 2 pi t, say, times the integral from t equals 0 to 2 pi t of V0 sine 2 pi f t dt. Well, I think you can see that if I integrated that from 0 to 2 pi over t, you'd get, in fact, 0, because there's just as much positive here as there is negative here, so it gives 0. So what they ended up doing is saying, okay, well, we're going to calculate the average of the square, in which case you're going to say 1 over 2 pi over t, integral of t equals 0 to 2 pi over t of V0 squared times sine squared 2 pi ft dt. That gives us what we'd call is V squared average. And then, of course, V root mean square literally means let's take the square root of the average of the square of the velocity, or excuse me, voltage. I don't know why I said velocity. I do, but I shouldn't have. So that's what that is. That's root mean square. So whenever you use like a digital multimeter and in AC and you measure the voltage or the current, it's giving you this quantity, what we call root mean square. And in fact, it equals compared to the actual peak to peak that you're seeing there, it actually equals V0 over the square root of 2. So when we say V equals 120 volts, what we mean is VRMS is equal to 120 volts, which means that V0 is essentially 170 volts. So it's actually has an amplitude of 170 volts, not the simple little 120 that we're talking about. Does that make sense, Michael?
Yeah.
Okay. So now the other part is, and this is the whole reason that we run those wires over country acres with 100,000 volts, 500,000 volts, 200,000 volts, 1,000,000 volts, that kind of stuff. Because if you step up the voltage, whatever factor you step the voltage up by, the current will be stepped down by the exact same factor. And since the actual power dissipated is the square of the current times the total resistance, and total resistance is proportional to length, so you can't do anything about it, then it's much cheaper to run a lower current and then use a step down transformer when you get to the neighborhood. So here's part B, where I'm asked to calculate what it is with 0.520 amps. But notice the 0.52 is a decrease in the amperage by a factor of 100, but an increase in the voltage by also a factor of 100. So now I'm going to put part B here, and this will be super straightforward. P is going to equal, and technically I should call that P average since we're dealing with, since we're actually dealing with AC. I'm going to say this is 0.520 amps squared. It's still 8. There I go, writing my one again, 8.106 ohms per mile times 100 miles. Okay, so in this case, we're going to get 0.52 squared times 8.106 times 100. And I think y'all can guess what the number is going to be. It should be 2.192 times 10 to the second watts. In other words, by increasing the current by a factor of 100, we decrease the power loss by a factor of 10,000. So yes, that is why we choose to use super high voltage to go long distances with the AC. And what you'll learn is as wire carries current, it creates a magnetic field wrapping around it, so that like if you hold your right hand up like I'm doing right now, where my right thumb is coming towards you, if that's the direction the current is going, then my right fingers are wrapping around the wire in the same direction as the magnetic field is pointing, so that literally right to the on this side of my current, it's going down. It's got electric field down. Over here, it's got electric field this way. To the left of it, or my left of it, it's got a magnetic field going this way, and then above it, it's got a magnetic field going this way. So you can actually use that current, or excuse me, that magnetic field, and create your own little loop of current and steal electricity from them. But the power company is really, really smart, and they can detect that super, super quick. But literally, if you just held up a big square of wire with a bunch of turns on it, that could generate electricity. Of course, it's also a little dangerous because you're actually going to have current all of a sudden when you don't expect it. So it could, obviously do all the damage that current can do. It only takes a milliamp to kill you. So that gives you a little bit of perspective. All right. Any questions on that? Okay, so what I've done now is I've now calculated basically a bunch of different things. What I really need you to understand from chapter 25 as a everyday American that might have to do stuff is to understand how we can use power to keep us quote unquote safe. So we've already learned, or I've mentioned to you about GFCIs, ground fault circuit interrupts, specifically how current going through an electromagnet, if the current gets high enough, the electromagnet gets stronger. Actually, anytime the current goes up, the electromagnet will get stronger. But if you get it to a certain strength, you could actually set it up so that at a particular strength corresponding to a particular amperage, namely, let's say an amperage that is just barely allowed for the wire you're using, then that magnet could pull a lever away from completing a circuit. That lever now not completing the circuit means the circuit's dead, no current is running through it, and that could protect your house from burning down. So we've got all sorts of neat stuff like that we've talked about. In this case, what you really need to do is you need to understand that a given wire gauge, like I just mentioned, number 10 gauge wire is only supposed to have 55 amps going through it at most. So you need to be cognizant of that. So if you go to Home Depot or worse, Dollar General or Dollar Tree or one of those type places, way worse, in fact, you can get extension cords that, well, they're cheaper partly because they're not made as well. And if the gauge of the wire is smaller than the equivalent one you would have gotten at Home Depot or Lowe's or something like that, or, you know, even more expensive place, you might actually find that what looks like two identical wires, but one's way cheaper than the other. The two wires aren't in fact identical. And in fact, the gauge could be too small for the one you got from the cheap place, and therefore only allow a much smaller current. So how do you know exactly how much current something has or is going to use, so that you can know whether or not you're using the right extension cord? Case in point, I once used a extension cord that had been marked, or at least marked in such a way that told me it was okay to use this, and I was using it for an edger, and in fact it melted right through the extension cord and through to my fingers and left a groove that took literally on the order of 6 months to heal. It was literally burnt through skin over 2 fingers that had just cut a groove right through my fingers as the hot metal wire had melted through the housing and went into my finger. So this is a real thing. So how do we do it? Well, it turns out that P, which I showed you in the last problem, the average is root mean square average times the voltage root mean square. So the current root mean square times the voltage root mean square gives you actual power. So that means if you want to know what the amperage going through a wire is, you can just divide the power by the voltage. So what I have here is 4 items: a light bulb burning 100 watts of power, a heater burning 1800 watts, a stereo burning 300 watts, and an air fryer burning 1500 watts. And I'm going to plug them all into the same circuit. And that circuit is protected by a 20 amp breaker. Okay. Back in the day, it used to be like a fuse, and they'd literally have a piece of wire that they had done a lot of tests with, made of a certain metal, that if the metal was made to the right size, then right at 20 amps, that wire would melt through, let's say at 20.5 or 20.1 or something like that. That little piece of metal would melt through and open the circuit, meaning no longer allow the circuit to run through. That's how fuses work. Now we use things like electromagnets and stuff like that to do it. But let's go about what we're doing here. So what I need to realize first is that light receptacles, and I told you this already, just at least hinted at it, light receptacles like this, where you have a long side, a short side, and that little thing, they normally are grouped up like this. And actually, if you look at them, you'll see that they have very specific directions about where you're supposed to connect everything. So in fact, what you can do is you can take one wire, and I never remember which one the long one is and which one the short one is. My daughter sent me something last night. She's taking a physics class at NC State, and I think she suggested that the instructor had told her the short one was the hot wire, and the long one was the neutral wire. So you can say that's right or not, I'm not really sure. And it doesn't matter too much for the point, but the main thing is just know that one of them's hot. And something else that's really bad about these receptacles is they're made sort of like this, and they sit in a little box, and the absolute best place to grab them is right here in terms of just the geometry of the setup. And that's exactly where the screws are that have the high voltage. So if you touch it there, it will knock you on your butt. So be careful. Do not attempt to grab the thing either here or here or here or here or here. Do not attempt to grab that thing. In fact, it's best, don't even work with this receptacle at all unless that whole breaker's off and you've already tested it with a meter. But beyond that, let's get rid of this. So what I wanted to show you about this is specifically the fact that these things are actually all wired in parallel. Because what will happen is you'll have, here's another receptacle, you'll have a wire that comes from this side and connects to this side. Okay, and you can imagine that connecting to the long side of the receptacle, and you'd be right, because it's always going to consistently be that. Similarly, you're going to have another wire coming from the short side going to the short side again, like that. And then the next receptacle will go off like this from here to this receptacle, in which case you have a circle, and then you have another wire coming from, say, here going to here. And all that goes back to basically a source of power that, instead of a battery, you'll have like normally you'll draw a circle and then you just draw a sine wave in it. That shows you basically that everything's in parallel, because you can see that the left-hand side, you could represent as the low voltage, and the right-hand side is the high voltage, and they're all parallel. Okay. So what that means is each of these acts like a resistance. Everything you've got plugged in here acts as a resistance, and all these resistances are in parallel. And since they're in parallel, that means 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over ... for however many resistances you have. The nature of this is R equivalent, which I'll put a P on it so we remember, in parallel is less than R sub I. In other words, it's going to be smaller than any resistor you have in the circuit. So as you put more and more loads, which are acting as resistances, the electric heater will act like a resistance, the stereo will act like a resistance. The more of those you put in it, the smaller the current, the smaller the resistance gets. And since V is equal to IR, as R goes down, I must go up, because V is equal to that VRMS, which equals 120 volts. So that's going to stay fixed. So that's what we're looking at here. So now I'm going to take and calculate what the currents are. And the way I'm going to do it is this. P light bulb, that was the first one I did, is equal to I light bulb times V light bulb, which means I light bulb is equal to 100.0 watts. And I'm going to assume all these zeros they give us are accurate, so our actual sig figs. So I'm going to divide that by 120. If you wanted to, you could be a little conservative and call it 125. 120 is usually enough, because I actually find when I measure it, it's normally closer to like 117, 118 than it is to 120 or higher. So I'm going to do 100 divided by 120, and I think I get 0.83. That's 0.8333 amps. So that's 833 milliamps is one way of looking at that. Now the the current for the next thing, which was the heater, is going to equal, again, we're going to take the power, which in this case for the heater was 1800 watts, and divide that by the 120. So 1800 divided by 120 is going to give me, okay, of course that messed up. 1800 divided by 120 is equal to 15. That's going to give me 15.0 amps. That's a big chunk of the 20 amp breaker that we talked about already. So that's kind of scary. I'm already up to essentially 16 amps. The current for the stereo, of course, will be quite minor. That's going to be 300. Ooh. And this little dot was supposed to be 120 there. So that's 300 watts divided by 120 volts. So 300 divided by 120. 300 divided by 120 is equal to 2.5. So I'm already up to 18.5 amps. Things are not looking happy. Now I get to the air fryer. Oh my gosh. Air fryer is equal to 1500 watts divided by 120 volts. 1500 divided by 120. That's going to be 12.5. So yeah, I just blew away that circuit. So hopefully the circuit breaker will kick in instantly when I plug in the last thing or the next to the last thing. In fact, if I actually turned in, if I plugged in the heater and the air fryer first, the circuit would already break because that's already exceeded 20 amps at that point. And that's exactly what they're there for. Okay. So this is what you do if you need to know how many amps your particular electrical device is using. You take the power rating, which is measured in watts, and you divide it by 120, and it's always 120 unless you're dealing with something like a dryer or a stove that runs on what we call 240. Okay, in which case you divide it by 240, obviously, but that's generally what's going on with AC. Any questions on that? All right, so I got about 9 minutes left. What I wanted to talk to you about was Kirchhoff's rules. I've already mentioned that for one thing, the resistance in series is equal to R1 plus R2 plus ... And what I mean by that is you can imagine a little battery being connected to a resistor, like this. And you're going to say that that should be equivalent to a single resistance R equivalent. And I'll just say sub S. Then that should be the case. You just add them up. Similarly, 1 over R equivalent in parallel is equal to 1 over R equivalent sub P. That's going to be equal to 1 over R1 plus 1 over R2 plus ... And in this case, what that means is if I had a battery here and a resistance R1, well, that looks horrible. A battery here, say, whoa, I just erased everything. A battery here, a resistance R1 here, and then a resistance R2 here, and then a resistance, whoa. I'll do it like this and just say ... That's exactly equivalent to having the battery in series, whoa, with exactly 1 resistor R equivalent parallel. Okay, so that's the result. You can look at the derivations yourself. They make sense, but basically what it comes from is that you learned in lab your series and parallel circuits that the voltage across resistor R1 plus your voltage across resistor R2 plus voltage across resistor R3, they add up to give you the voltage, the total voltage, which is the voltage of the battery. And because each of those voltages can be given by I times R, and that each of the currents going through R1, R2, and R3 are the same. Therefore, the I's cancel out and you just get R equals R1 plus R2 plus R3. Similarly, in this case, the currents in the parallel, the currents add up. So the current through R1 plus the current through R2 plus the current through R3, they all add up to give you the total current coming out of the, let's say, not only the battery, but the battery with just the equivalent resistance. So in that case, from Ohm's law, I is equal to V over R, but all the voltages are the same. So you end up getting 1 over R is equal to 1 over R1, so on and so forth. That's actually how that works. And I've wasted only 2 minutes of my time. So now what I'm going to do is I would like to try to start off working a problem for you. I hinted to you guys how to actually go about doing your microscopic view of electric current. In other words, how to calculate the number of charge carriers per unit volume. So you should know how to do that, even though it's not really, I didn't show an example, but I did show you how to actually do it. So I'm not going to show you an example, at least not right now, of resistances in series and parallel. But what I am going to do is solve using Kirchhoff's rules some resistor problem or some circuit problems. So this is one of the multi-equation things you have to be able to do for this physics class. If you have a circuit, for instance, you have to be able to figure out what is the current through all the different parts. So what I'm going to do here is I'm going to show you, let's stop sharing the screen. I'm going to show you a problem from the textbook. And it's this right here. So what you can imagine is in this scenario, you have a starter motor, which again, all electric things, you can sort of treat them as a resistance. Now that resistance could change at different temperatures, at different currents, at different heats, and so on and so forth. But the main thing is you can treat them as a resistor to some extent. And what's going to happen here is I've got a battery, a weak battery with an internal resistance of 0.01 ohms. That's what this is. We've discovered that if you imagine a battery as a perfect battery whose voltage never changes, you find out that doesn't fit reality. But if you imagine a real battery to be that perfect battery with a resistance internal to it, and then you can pretend that that internal resistance is going to increase over time, that fits reality pretty well. So that's why we have these little internal resistances. But what we're going to do is we're going to take this weak battery that would normally be used to start this engine of the car, and we're going to put it in a jumping situation with another battery. So notice the positive side of the battery, which is the long leg, is lined up with the positive side of the battery. In other words, you're connecting positive to positive with jumper cables. Okay. Now you're also, this is normally what a lot of people do is they'll take the negative side of the good battery, connect it to black, and then you'll take the black side of your jumper cable and attach it to the weak battery. But in fact, most people now recommend that you take the black side, and instead of connecting it to the weak battery's black side, you actually connect it to the frame of the car or something like that, because there is a small chance that there could be some leaking and sparking that could ultimately result in a fire of some sort. So let's pretend like we know these actual resistances in this in this circuit. This problem is actually asking you to calculate it, giving you the gauge of the wire. And I want to use this example to show you how to use Kirchhoff's laws. So what I'm going to do is I'm going to draw this circuit right now, and I'm going to put some resistances in it, and I'm going to show you how I could go about analyzing it. So first off, I've got a starter motor that really is somewhat irrelevant to the whole situation, by the way. The starter motor is. So there's my, and I'll show you this in a second, but I got to draw it first, folks. So I'm going to take a wire and we'll pull it from there. I'm going to go up. I'm going to run into a internal resistance like that. And then that's going to run me into a battery. I'm just talking to myself. Yeah, I know y'all can't see me. Let's call this a nice even 10.0 volts. And let's say this internal resistance is 0.010 ohms. Okay, that's lowercase r. Actually, in fact, let me not write that so close because that really looks bad. And let's call this 0.010 volts. And then outside of that, that comes back here to the power supply. Now, what I'm going to do is I'm going to say that this wire has a resistance of 200.0 ohms. That's what I'm doing for the jumper wire, and I'm going to do the same thing for the other jumper wire. Obviously, from the calculations we just saw, that is not a reasonable assumption, but I just needed a figure to put up there. And now I'm going to put another resistance. This will be R2 is equal to 0.020 omega ohms, that is. And that's going to be connected to a battery that's actually at 12.5 volts. Okay, now I can share the screen because I've got everything drawn on here. So let me stop share here. And let me start sharing. We're right at the 40-minute mark. What I want to show you is this real quick. Kirchhoff's voltage rules, or Kirchhoff's loop rule and Kirchhoff's voltage rule basically say, what the heck? Crap, I didn't do it. They basically say that if I go in any closed loop, so like I'm going to pretend right now that there is a current I1 going through here, and I'm going to pretend there's a current I2 going through here, and then that produces a current I3 going through here. At that junction, you've got two sets of charges coming in every second. So you assume that I1 plus I2 has to equal I3 just as conservation of charge. Well, that's called Kirchhoff's junction rule. Not only that, if I imagine going, let's say instead of I2 going to that direction, if I had I2 going this way, I think you'd understand that I2 going this way suggests this should be a voltage drop going this way. But when you're using Kirchhoff's laws, Kirchhoff's loop rule, what you're supposed to do is when you go the direction of the current, then the voltage across the resistor is a drop. When you go the opposite direction, damn it, my dog, sorry. When you go the opposite direction, it's a voltage increase. So that's the main thing that you got to get out of Kirchhoff's loop rules is if you go from negative to positive on a battery, that's delta V being greater than 0. In other words, it's positive. If I went this way on a resistor, that's delta V. Notice the current is actually going to the right here. So I'm going in the opposite direction. So in that case, the delta V is less than 0. In other words, it's a negative. You just use Ohm's law, V equals IR. So you'd say I1 times 0.010, and that shouldn't have been volts, that should have been omega. I1 and 0.010 multiplied should give me the change in voltage, and that's how that works. So let me get rid of this up here too. I know I don't want y'all to see that later, but the main thing is I was trying to explain Kirchhoff's loop rule. I don't want it in that color. Kirchhoff's loop rule just means that when you go in any circle, delta V, the sum of those equals 0. Okay, this means the sum of the currents in is equal to the sum of the currents out. And that's it. You guys are free to go. I'll wait for the last person in case anybody has any questions. I apologize for running you over again by almost 3 minutes now. But anyways, hopefully that's good enough. We'll actually solve a couple circuits next time, and that's mostly what we have to do for chapter 26. I'll do a little bit more, but I think I'm going to push your chapter homework back and from Tuesday being due Monday night at 11:59. I'm probably going to push that back to being due at least Wednesday night, if not a whole nother week, just because we're a little bit behind. So have a good one, folks. Again, I'm going to wait for the last person out in case anybody has any questions.
I have a question.
Yes, go for it, Joseph.
So in the homework, there's a problem I got really stuck on. I'm gonna put it in the chat so you can look at it.
Okay.
There you go.
Okay, I've got the chat. Okay, it says in the figure, let C1 equals 4 microfarads, C2 equals 6 microfarads, C3 equals 7 microfarads, and V equals 12 volt. What is the potential difference across each capacitor? Okay, were these capacitors in series or parallel? Or a mixture?
I think it was in a parallel.
Okay, so if they're all in parallel, then all the voltages will be the same and all the voltages will be 12 volts. But what you have to use to finish this problem, to actually do this problem, I'll pull it back here. What we're using is C equals Q over V. So if we had, for instance, a 12-volt battery, I'm assuming this is what the problem was, then it would run off to a capacitor like this that has a capacitance of, let's say, 4.00 microfarads, and then another one that has 6.00, whoa, 6.00 microfarads, and then another one that has a capacitance of 7.00 microfarads. Does this look like the picture you had?
Yeah. So it was it kind of had like, yeah. So V was on the bottom, 12.0, and C2 and C3 was on the same line. So there's two of them. Then the very top was one.
C2 and C3 were on the same line, and then C1 was like parallel to it.
Gotcha. Yeah, so it was on top, and then the volt was on the bottom. Yeah.
Gotcha. So C1 and C2, that would have been the 4 and the 6. And then these were in parallel with that 7 one.
Yeah. Yeah, it was actually 6 and 7 instead of 4, because 4 was C1. C1 was on top, so it's actually yeah, because C2, C3, then it's volt, and then C1 on top and volt on the bottom. So it was on the bottom. It was 12.0 for the volts. In the middle was 6.00 and 7.00, and on the top is 4.00.
Okay, so the 6 and the 7 were next to each other.
Yeah, I'm sorry.
That's okay. Yeah. So it was more like this then.
Yeah.
Okay. So what you do is you first attack this and say, okay, we've got a battery. This guy is 4.00 microfarads. We can tell it's a capacitor, so you really don't even have to write the F there. But that's going to be actually in parallel, which is actually the easier thing to calculate. But in this case, we got 1/6 plus 1/7. Obviously, you can jump to calling this 7 plus 6 over 7 times 6, which would be 42. So that would in fact be 1340 seconds. So the equivalent capacitance over here would be 42/13 microfarads. Just quickly doing that number, let's see, 42 divided by 13 is equal to 3.23. 3.231, say, microfarads. Now we've got these two in parallel. So you'd say, okay, well, this is equivalent to one capacitor that is 7.231 microfarads total. in series with a 12-volt battery. And what that tells you is that allows you to figure out the total amount of charge that leaves the battery. So C equals Q over V means Q is equal to 7.231 microfarads times 12.0 volts. So plus 4 here times 12. That gives me 86.77 microcoulombs. That's the total amount of charge that left here was 86.77 microcoulombs. And what that means is that's going to break up into Q2 and Q3 such that V, the voltage for the 4 microfarad capacitor, has got to equal the voltage for the 2, the total voltage for the 2. Okay. So with that, you can say, okay, well, I know that those 2 are equivalent to 3.1, or excuse me, 3.231 microfarads. So I can say, okay, well, voltage is supposed to equal Q over V. So I can say Q sub 3 over, well, actually, they're both going to be 12 volts. So I don't even have to do all that. Sorry about that. Okay, so each of these is 12.0 volts. So that helps me. So the voltage for the 4.00 microfarads implies the Q for the 4.00 is actually equal to 4.00 microfarads times 12.0 volts, which is 48.0 microcoulombs. So that's how you get one of the answers. Similarly, we know that the equivalent capacitance is 3.231 with 1 extra sig fig microfarad. So in this case, the charge on, and remember the way the charges work when they're in series, whatever charge comes to the left plate of that 7 microfarad capacitor, that same charge will leave the right plate and end up on the left plate of the next charge. So the 2 charges for these, for the ones in series, are actually going to be the same. So Q 7.00 equals Q 6.00 is actually equal to 3.231 microfarads times 12.00 volts. So that gives me 38.77 microcoulombs. So that's the actual answer for the other one.
Okay, that makes sense now. 38.77. Okay, that makes a lot more sense now. Okay,
Yeah.
I was doing it totally wrong.
It's a little weird, but what you got to figure out is, first off, hey, let's make the equivalent capacitance, because once you get it to 1 capacitance, you know the total charge is leaving the battery. And then you say, okay, well, I remember that all wires, if you remember from the first lab, or excuse me, not first lab, but when we did graphing electric fields, what we discovered is that the surface of a conductor, like the little white things that were on that carbon page, that's an equal potential. So what that means is, let me draw it with a different color so you can see what I'm talking about. I'm going to use blue here, but that means this wire has a voltage right here about 12.0 volts. And if you go anywhere along here where I haven't put a separate resistor, that too is also at 12.00 volts. Now, technically,
Right.
its current flows through there. It could be a little bit smaller because the wire has a little resistance. But once it's in equilibrium, then all the voltage that's blue is all equal. The same thing happens on the
Right.
other side. This one is 0.0 volts, but that means this right here, I really should do a different color here. So let me do green. So this one right here gives you the voltage all the way up to here. That's why I knew that the voltage across the 4 ohm resistor, or excuse me, the 4 microfarad capacitor was in fact 12 volts. And that's also why I knew, as you can see here, that the total voltage across the equivalent capacitance, which is this guy right here, was 12 volts.
Right.
So that's why I used the 3.231 in there to figure out what the ohms were in there. But and just remember, like I said, when they're in series, you get a plus Q, and then the one that's facing it, that plate's going to be minus that Q, and then that next plate will be plus Q again, and then that next plate will be minus Q again. So as long as they're in series, all the Qs are equal.
Right. All right, that makes sense. I just put the answer in the 12.0, 48.0, and 38 .77. I put that into the Pearson, and it's still showing it's wrong.
Send me a photograph of the picture, and if it's multiple choice, send me a photograph of the picture along with the actual answers. I suspect there might be something slightly different than my diagram here, if that's the case, or I made it just a careless arithmetic mistake. But I stated basically the physics right. What I'll do is I can make an actual problem out of it and post it on my YouTube channel as just a standalone problem, and that'll help you. So go ahead and take a picture of it, and I'll straighten out whatever's gone wrong with this solution. Okay.
All right, do you want me email it to you?
Yeah, just email it to me. That'd be good.
All right, I'll take
I'll try
that.
to do it before Friday.
Yeah, I can email it to you probably tomorrow, tonight, probably
No
tomorrow.
problem. All right.
Yeah,
Thanks.
even though it's due tonight, but I'll,
Is it due tonight? Well, I will
Yeah.
actually, that homework, is that chapter 25 or 24?
No, it's 24.
Okay. Yeah, give that a try, sort of like the way I did it, and just look, see if you can solve it yourself. Maybe I made an arithmetic mistake somewhere, but basically what I said was right. If that diagram's right, if you send it to me now, I might be able to give you some idea and tell you where I went wrong.
Right.
Okay, so just you can text it to me, or you can email it to me. That'll be fine.
I'll text it to you, make it more easier.
Thanks, Joseph. Have a good one.
Yep, you too.
I think that's the last person here, so let's end it. Awesome.